Number 64. The sugar fructose contains 40.0% carbon, 6.7% hydrogen, and 53.3% oxygen by mass. A solution of 11.6 grams of fructose in 325 grams of ethanol has a boiling point of 78.59 degrees Celsius. The boiling point of pure ethanol is 78.35 degrees Celsius, and the Kb for ethanol is 1.20 degrees Celsius per molality. Assuming ideal solution behavior, what is the molecular formula of sucrose? Strap in those shoes, my friends, because we're going for a wild, wild, wild ride. Fun. But we got to do it. We got to, go through this problem. We got this. So the first thing that I see here is, whoa, we got a lot of numbers, right? We have percent values. They told us that we have 11.7 grams of fructose, right? And it's a solution. It's in ethanol. It's got a boiling point. And, at the end of the day, they want that molecular formula. Now, the main thing that I'm interested here for now is that they gave me percents. And they gave me percents of each individual component. Now, if we just forget about all of this, right, and we see that we have percents, and they're asking for the molecular formula, that's a very big slew of steps that we have to do, especially if they give you percent and they're asking for either empirical or molecular formulas. Because from percent values, to find a molecular formula, we could always follow the progression of this right here. It's a huge progression, but it will get the work done. We can always start from a percent value and go through all the steps to finally get the molecular formula. Now, are there going to be bumps along the way? Of course, for this question, but I'm with you every step of the way. So, we have percents. So let's just list them out. So we got 40.0% carbon. We got 6.7% hydrogen. And we got 53.3% oxygen. Now the first thing is, especially if they give you percents, make sure that there's no hidden percentages here. So I would always just quickly, add these up just to make sure that it equals to 100%, and it does look like it does equal 100%. So there's no hidden percents here. So we have everything that we're working with. Now the first thing is that we just have to convert the percents into a gram value. They did say that these percents were by mass. So that's how we can go from percent to gram. Now we assume that the total percentage is always equal to 100%, right? So if we have a 100% sample, I can kind of translate that to saying that my total sample that I have is equal to 100 grams. And because of that, if I have a total of 100% sample, which equals 100 grams, this 40% will equal 40 grams. The 6.7% is going to equal 6.7 grams, because the percentage is always going to equal the grams. So that's how we get it into grams. So in this case, we have 40.0 grams of carbon. We have 6.7 grams of hydrogen. We have 53.3 grams of oxygen. So we have successfully went to the next stage. Now we want to go from the grams to the moles. This is going all the way back to beginning of stoichiometry, right? Grams to moles, you're always just going to divide by your molar mass. And the molar mass is found on the periodic table. So I can go from grams of each of these to moles. So moles of carbon, moles of hydrogen, moles of oxygen, by dividing each one by their molar mass on the periodic table. And notice here that I'm doing each step together. I'm not taking carbon and going all the way to the end, right? I'm doing each one of them, I'm grouping all three of them, and I'm moving together. So we find all the moles. Then we move on all of them to the mole ratio. So let's just go on the periodic table, find out what these molar masses are. For a carbon, it's 12.01 on my periodic table. For a hydrogen, it's 1.008. And for an oxygen, it's purely 16. So I'm going to take my 40 divided by 12.01. And I get roughly 3.33 moles of carbon. 6.7 divided by 1.008. It's roughly going to be, 6.65. You can cut these off after a couple of decimals. 53.3 divided by 16, we get 3.33. Okay. Now, we're at the moles. We want to find the mole ratio. Now, a ratio is always a fraction, right? So we could have said mole fraction, we could have said mole ratio. So I know that I'm going to take these moles and divide it by some number, because that's how we make a ratio. But now, let's use the information that the next step has to get to what we're supposed to divide by. Now, any time that you want to find an empirical formula is always the lowest possible subscripts. Subscript. That's what an empirical formula is. It's your formula, but just in the lowest possible subscripts. So, in order to find the mole ratio, we are going to divide, because that's what a ratio is, division. We're going to divide by the lowest moles. So we scan these three values, 3.33, 6.65, 3.33. Seems like the lowest is 3.33. So I'm going to divide each one by the lowest number, 3.33. Two of them, so I'm going to just equal this out. Two of them I already know the answer is 1, right? So I get 1 mole of carbon and 1 mole of oxygen. But if I just take, this number that I found and divide it by the 3.33, the specific one, I get a really close number to 2. At your mole ratio, you want to have whole numbers. If you can say that you can, confidently round to a whole number, go do it. So this would be 2 moles of hydrogen. So now the empirical formula is just putting all of these together. So I have 1 carbon. I could put the 1 there, but I don't have to. 2 hydrogen, so I have to put a 2 here, and then an oxygen. 1, but you don't have to. And voila, we have the empirical formula. We need that molecular formula. We are 1 step away from answering this problem. But I did say strap yourself in, right? Because do I know the molecular mass? Now, generally speaking, if we want to find the molecular formula, all we have to do is take our molecular mass, and maybe I'll do that because this is the next step. Our molecular mass and divide it by our empirical mass. The empirical mass comes from the empirical formula, and the molecular mass comes from the molecular formula. Now, I do know my empirical mass, right? My empirical mass is just going to come from what the CH2O is. Now, I just have to add them up, right? I have 1 carbon, so that's 12.01 on the... actually, I guess I'll do it down here, right? The empirical mass is coming from the CH2O. So if I just lay this out, and maybe I'll bring this over here. We have C, we have H, and we have O. I got 1 carbon, so on the periodic table, that's 12.01. I have 2 hydrogens, so 2 times 1.008. And then I have 1 oxygen, which is just 16. And we can add them all together. So if I just add these, bring this down a little bit, we can find the empirical mass. So let's see, 12.01 plus 2 times 1.008 plus a 16er. That looks good to me. I get an empirical mass of 30.026. So this number down here is 30.026 grams per mole. But the thing is, I'm stuck because I don't have that molecular formula to know what my molecular mass is. So this is a question mark right now. We've done all that we could to solve, for everything that we can with the percentages. And that's it, guys. I got nothing left for you, so good luck. Just kidding. Just kidding. Because now we use the next piece of information. So we've used all that we could with just these percentages. So maybe what I'll do is I'll just put a line here, because I'm going to now start, working down here. Okay, so now they say that we have a solution of 11.7 grams, okay, of the fructose in 325 grams of ethanol, and we have a specific solution boiling point. They tell us that the pure boiling point of ethanol is 73.35 degrees Celsius. Now I say to myself, what formula am I going to use here? They gave me a Kb value. This is the boiling point elevation constant because it has units. This Kb is not your equilibrium constant for a base because those values do not have units. So if you see that you have a Kb with units, degrees Celsius per molality, that's your boiling point elevation constant, and that only goes with one formula, and that's this formula right here. So let's just put it over here. Delta TB equals Kb times M times I. Now let's see. Delta TB is the change in the boiling point. Do we know that? Well, yeah. They told us that the solution had a boiling point of 78.53, and the boiling point of just the ethanol, the pure ethanol, is 78.35. So there is a difference here. That's the same thing as a change. And just know that your delta TB can only be a positive value. So you have to subtract these two numbers in which you get a positive value, higher minus the lower. So we can take our 78.59 degrees Celsius and subtract it from the 78.35 degrees Celsius. 78.59 minus 78.35, and I get a delta TB of 0.24. Now I'm starting to realize that, having all of this information up here, I need to get rid of some of this stuff because I just don't have enough room. I don't think that this is going to be enough room for all the math that we still have to do. So what I'm going to do is just pause the video if you need to. I'm just going to get rid of this way down here because we don't need this anymore. We basically did all this information to get that empirical formula, which we know is CH2O. So unfortunately, bye-bye. So I'm just going to bring this up now. So what I'm going to do, we're just going to make this a little bit better. And there we go. Okay. So we have a delta TB, check. Do we have a Kb? Yes, we do. The Kb is solely reliant on the solvent. So since we have a Kb for ethanol, and the Kb is only for a solvent, we know that the ethanol has to be the solvent. That's going to come into play probably in a little bit. But they did tell us that we had a Kb value of 1.20 degrees Celsius per molality. So now we're down to M and I. Which one do I not know the answer to? Well, molality, right? Molality equals the moles of the solute divided by the kilograms of the solvent. The only thing that they gave us was that they gave us 11.7 grams of fructose. But once again, I run into a problem because they said it was fructose, but I don't know what fructose is. I don't know what that formula is. That's what we're trying to find out. So I can't convert these grams to moles because I don't know the chemical composition of fructose. I know the empirical composition, but I don't know if this has to be times by 2 or by 3 or by 4. So I can't find the molality, which probably means that we're going to solve for it. So that means that we do know the I value. And the I value is called the Van 't Hoff factor. This factor, the I value, determines whether your solute is a non-electrolyte or an electrolyte. Now, we said that the ethanol was the solvent. And in our solution, we have fructose going into the ethanol. The solute always gets dunked in the solvent. And if the ethanol is the solvent, that means that the fructose is the solute. So, for non-electrolytes, a big thing here is that if you have a covalent molecule, this is going to be a non-electrolyte, meaning that it's just not going to have any electrical activity. It's not going to be able to turn a light bulb on if you have a probe in the solution. And if you have a non-electrolyte, your I value is going to equal 1. For electrolytes, your I value will start with 2. Could be a 2, could be a 3, and that just depends on how many ions are in the solution. But I know my empirical formula has everything to do with carbon, hydrogen, and oxygen. Those are all nonmetals, and all nonmetals are covalent. So we know that we have an I value of 1. So it was really great that we actually did this part first, because then we can say, okay, we had C, H, and O. They did tell you that you just had carbon, hydrogen, and oxygen as well up here. So you could have found out that, okay, since these were the only elements, it was a non-electrolyte as well. So we have the I value, we have the Kb value, we have the delta Tb. We're going to solve for the molality. So maybe I'll just put it over here. So 0.24, that was the delta Tb, the change, equals Kb, which was 1.20, times x times by 1. Doesn't really matter, 1 times 1 is the same thing. I'm going to get x by itself. I'm just going to divide by the 1.20. Okay? And we get our molality. 0.24 divided by 1.2. Okay, so I get x equals a 0.2 molality. But now how is that going to help us? We still want to find that molecular formula. Well, do we know a general formula for molality? Yes, we do. We talked a little bit about it before. But molality equals the moles of the solute divided by the kilograms of the solvent. Anytime that you're trying to use a formula, you have to know all of the variables except for 1. And we just found out the molality, 0.2. So maybe we can solve for the moles, or maybe we can solve for the kilograms. Let's see. They told us that we had 3.25 grams of the ethanol, and that's the solvent. So we know that we have 325 grams of the solvent, and which is the ethanol. So grams to kilograms, I can do that, right? Grams to kilograms, all you got to do is just divide by 1,000. Similarly, take the decimal, move it to the left 3 times, and you get 0.325 kilograms. So we know this value. We know the molality, we know the kilograms, so we can solve for the moles. So let's do it. 0.2 equals something over something, x divided by the 0.325. Okay, so cross multiplication, 0.2 times 0.325, and we will get the moles. 0.2 times 0.325, and I get 0.065 moles. And that's specifically of the solute, and we did say that the fructose was the solute. Okay, now where are we going to go from here? Remember, we still want to get that molecular mass. This was where we were having a little trouble from before. So now I say, okay, let's see. Molecular mass. Molecular mass is the same thing as molar mass, right? And any molecular mass or a molar mass, so maybe I'll just put that over here, molecular mass or molar mass will always equal the grams that you have of the substance divided by the moles. Now in this case, we still want to find out that molecular mass of the fructose, right? So it would be the grams of the fructose divided by the moles of the fructose. Did they give us a gram amount for the fructose? Yes, they did, right? They told us that we had 11.7 grams. So I have 11.7 grams. And the moles that I just found out was of fructose. So this is 0.065 moles. Oh my goodness, we are about to bridge the gap between the two parts of being left off here and now using all this information to find out that molecular mass. 11.7 divided by this. And we have bridged the gap. Now we know that that molecular mass is 180 grams per mole. So going back to here, I now know that that molecular mass, this ain't no question mark anymore. It's 180 grams per mole. So let's see. I told you this was going to be a wild ride, guys, right? This is a decimal. I guess it's over here. I'm just trying to maybe make some more room because we have a little bit of room here. And we're almost done. So what we're going to do is we're going to take that molecular mass, the 180 grams per mole, and divide it by the empirical mass that we found out, what, like 3 hours ago? Guys, if you're still here and you haven't subscribed, please, thank you so much. But anyway, let's just keep going. 30.026 grams per mole. Okay. So, now let's do the math. Now, what is this really going to tell us? This is kind of like a ratio, once again. It's going to tell us how much larger our molecular formula is from our empirical formula. So, let's see, 180 divided by 30.026. Should be relatively a whole number. I mean, we got 5.99, so this is going to be 6. This means that my molecular formula is 6 times larger. So, we had an empirical formula of CH2O. We now know that our molecular formula is 6 times larger. Those go for the coefficients. Sorry, those go for the subscripts. I'm just getting really excited that we're almost here. We're almost at the end of the question. So we're going to times 6 by all of our subscripts. And we get C6. H, 6 times 2 is 12. O6. And oh gosh, we have finally found that molecular formula. And fructose is C6H12O6, right? If you guys have taken biology, biochem, but that would be probably after this course if you are taking biochem. Fructose is a simple sugar, C6H12O6. It's a monosaccharide. It is the predominant sugar that's found in fruit. So fruit, fructose. Thank you so much for helping us out. And by, subscribing to the channel, watching the video, telling your friends, telling your classmates, thank you so much. And I really hope this worked out. I really hope this helped you out. A lot of concepts in this one. So you're awesome. You rock. Thank you so much for being here. I really do appreciate you guys. And keep studying hard, okay? Always keep learning. And good luck on your tests and quizzes. I'll talk to you soon in the next lesson, okay? All right, bye.